And here we are with the 2-3 day 1 assignment. There's some book work, and then we also have a factors worksheet. In these first few problems, there's actually kind of a lot going on that's being asked of you, as you can see in the directions paragraph. But we're first going to describe how to transform the graph of an appropriate monomial function into the graph of the given polynomial function. And we're going to sketch that transformed graph by hand and support our answer with a grapher, and then compute the location of the Y-intercept. So we are going to kind of shimmy through this whole sketch the transformed graph by hand idea. And so I'm going to show you an image of what it is, but you're either going to do it on Desmos or on your graphing calculator. I don't often say Desmos, but for these with transformations, it's a lot easier to kind of see them on Desmos versus on your graphing calculator. Either way, and then we'll compute the location of the Y-intercept to check this. So taking a look at number 2 here, I guess I'll go over here. We are looking for how this transforms from x cubed itself. Okay, so taking a look at actual x cubed, it does just go through the origin in kind of this snake-like shape. So that's what's happening with x cubed itself, but then notice that this new equation is saying there's a negative here as our a value, and then there's a plus 5 here. So what happens is the plus 5 moves this equation to the left 5. So instead of at 0, we're going to be at 1, 2, 3, 4, negative 5. And so our new equation will have that intercept right here instead. And then the other piece is that we have this negative out front, which flips it across the, let me think about it, x-axis. So we're going to flip across the x-axis, and so now instead of going up and to the right, it's actually going to go down and to the left. So ultimately, we're going to end up with this graph versus the original. All right, so this again was x cubed, and then this one is your transformation. Okay. Again, the description of what's happening here is that we're moving it left 5 and flipped across x-axis. So taking a look at what it's wanting you to do, we've got graphing the given polynomial function, that's in blue, sketch the transformed graph by hand, so that's in blue, and then we have the original in green, and then we need to compute the location of the Y-intercept as a check on the transformed graph. So the idea would be that whatever the Y-intercept would be, it would be shifted via this left 5 and this flip. Because this is such a fast-growing cubic equation, it's going to grow pretty quick, pretty fast. So if we want to go ahead and solve this to find our y-intercept, so that means where it's going to have an x of 0, we would just plug in a 0 for the equation. So here we are with g of 0. Is going to have a negative and then 0 for our x, plus 5 cubed. And still, let's see, 0 plus 5 remains 5. And so we're really just doing 5 cubed, which I believe is 125, and then the negative stays. So our y-intercept is going to be 0 for our x, negative 125. So way down at the bottom. All right. The next one that we're doing here is number 3. So we're going to do it in the same way. We're going to graph it, having checked out each of the pieces. And all of these first 3 here are from x cubed. So we still have our x cubed equation going through 0. That was bad. Going through 0, 0 there. And then we take a look at each of these pieces. So The first piece that I'm seeing is a negative, okay, and so that negative is going to flip it across the x-axis. That second piece is the half, and so that's going to reduce, actually we'll just say shrink vertically. The next piece is a plus 1 inside, and so that plus 1 means we're shifting left 1. And then the last piece is a plus 2, and so that means we're also shifting up 2. I think the easiest part to start with is the fact that 0, 0 used to be our initial rotation point, but now we're going left 1 and up 2. So we now have a function that would have that as its rotational point. We also know that from that negative out front, we're actually going to be flipping this graph, so it is going to go down from left to right. And then we also know that it's going to be shrunk vertically. And shrinking things vertically actually makes them wider. So you could also say widened horizontally. And so in that case, I'm going to take out these little dots that I just made and make kind of a more wide graph. Usually with the widening part or shrinking vertically, it's going to be kind of hard to visualize and replicate on this graph, but we did say shrink vertically down here, so if we can't necessarily see it equally in the graph, then you at least have it written. The other piece is your y-intercept, and so again we're trying to find out what 0 is for this equation. And so if we plug in a 0, we'll have negative a half, 0 plus 1 to the third plus 2. And so if you do the algebra appropriately, you have a y of 1.5. I kind of have that in here. 1.5, I suppose that would be here. So if you want to erase that piece. So definitely wider when you look at it that way. All right, and so then the y-intercept, just to be clear, is 0, 1.5. All right, number 4 I'm going to do on another page. So here we are with our next graph, and again there's a cubic parent function, so we would be looking at these here as our x cubed, and then taking a look at each of the pieces. That 2/3 there is going to, it's less than 1, so it's going to shrink our graph vertically, which again just means that it's going to widen, because shrinking vertically is the same as the opposite of stretching horizontally. So, and then we have our subtracting 3 in with that x. So if we're going to subtract 3, you feel like that's left 3, but it's actually shifting to the right 3. And then that plus 1 is going up 1. And so again, as we did in the previous one, it's nice to just start with the fact that it was at 0, 0, but now it's going right 3 and up 1. So 1, 2, 3. So that's the new center of that rotation of the x cubed. And then we're going to shrink it vertically again. So in that case, again, it's going to get wider. And so I'm going to be kind of exaggerating here. And actually, before I continue this, I'll just go ahead and find the y-intercept, because then I can figure out where I'm going to go through that axis. So the y-intercept plugs in a 0. So g of 0 is what we're looking for, which will come from 2/3, 0 minus 3 cubed plus 1, or 2/3 of 3 cubed, which is 9. And so we actually have 6 plus 1. Okay, so apparently the y-intercept is going to be at 0, 7. So let me think about how that works. And by 0, 7, I mean negative 3 cubed is actually negative 9, so it's negative 6, and so it's negative 5. Okay, so that makes more sense. So 0, 1, 2, 3, 4, 5. So this graph is going to come down like that. Oh, that was really weird. It's like a sneeze. Okay, I like it. That's perfect. Okay, so again, that's your transformed or new graph, wider, and then at a different center of rotation. All right, then if we move on to number 5, and so this is our equation for number 5, and instead of the cubic function, we're now starting with the quartic function, which would be to the power of 4. And so let's see how this works. Kind of, oops, wow. Kind of looks like a wider squared graph when you think of x to the 4th. All right, and so if we're going to, again, take note of each of these pieces, the negative of the negative 2, just gonna be weird here, the negative 2 is going to flip it across the x-axis. The next piece, the actual 2 itself, is going to stretch the equation vertically. And so it is going to look a little bit more like the x squared graph versus the x to the 4th. Let me double check. No, it looks like x squared is actually more like this in accordance with the graph I just made. Okay, so either way, it's going to stretch it vertically, and then from there we're going to see the plus 2, the x plus 2, which ends up saying that we're moving left 2, and then the minus 3 at the end means that we're going down 3 from that original 0, 0 intersection or origin. So again, taking that left 2 down 3 first, that's going to be kind of our new 0, 0, and then we're flipping it across the y or x-axis, and so that means that it's going to go down that way, but then we're also stretching it vertically, so instead of being as wide as it was before, it's going to be a little bit more narrow, so that image versus the yellow parts. All right, then officially the y-intercept, I assume, is going to be very negative. So let's see. G of 0 is going to get us negative 2, 0 plus 2 to the 4th minus 3. And so we're really going to take negative 2 times 2 to the 4th. 2 to the 4th is 16, so negative 2 times 16. So negative 32. So yeah, negative 35, which is kind of large. So our y-intercept is going to be at 0, negative 35. So I'm not really going to even be able to picture that on my very small graph, but you can see that it would be, in fact, down here at negative 35. So, sweet. All right, then we have one more of these, so number 6. So looking at our initial of the cubic function again, quartic function as the parent, that 3 that we have at the beginning is going to stretch what we have originally as the parent vertically. The x minus 1 is going to shift the equation right 1, and then the minus 2 is going to shift it down 1. So our new origin is going to be right 1 and down 1, so just over here, and then stretched vertically, so skinnier than the previous one. Taking a look at what I've drawn, I probably have a y-intercept that I could calculate. So that would be on this visual graph. So 3, 0 minus 1 to the fourth. So it looks like negative 1 to the fourth is just 3 times 1. So 3 minus 2, or 1. So apparently our y-intercept is going to be 0, 1. So it looks like I kind of drew it, yep, not appropriately. It looks like it should go like that more than as wide as it was. Okay, so anyway, a little bit less wide, the black equation here versus the blue one. And of course that's why when you are graphing by hand, you'd want to be as specific as possible, and in this case you definitely can be even in your sketch because you know where the y-intercept is, and then of course you know all of the pieces of how it shifts around. Alright, moving on to the next piece, we're going to match the polynomial function with its graph and explain our choice. We are not using a graphing calculator, so don't just type this in and say, hey, yep, there it is. We're actually going to use our logic here. So first of all, we have 2 cubic functions, and then we have 2 quintic functions. And so remember the idea from our notes that if you have a certain degree, that means that you have a certain number of options for intercepts, or a certain number of options for maximums and minimums. So for here, we can have at most 5 x-intercepts, and then we can have at most 4 maximums and minimums. So if we take a look at that in general, you can see, for instance, here we have a local max, a local min kind of idea, a local max, and a local min. So this one here can clearly not be 9 or 10. So in looking at the power, and then even looking at kind of this hiccupy area over here, that actually means that part A and part D are going to be either number 11 or 12. So we at least can identify initially that A and D are to the 5th power, and B and C must be the cubic functions. Let's see, after that we have a lot of different ways we could go about this, but the best way would be, as we saw in the previous example, to plug in a 0 to find your y-intercept, because each of these does have a different y-intercept. So if we plug in a 0 in for number 9, it's nice because all of these pieces will cancel except this last piece. So we know that the y-intercept for number 9 is 0, 104. Of course, looking at each of these, they are actually going up by hundreds. So for instance, this is negative 100 and this is 100. And so if I want to intercept at 0, 104, that's actually very close to this piece here. So that's why I'm going to go with this one being number 9. If that one's number 9 and there's only one other that happens to be a cubic, then this one's going to be number 10 by process of elimination. Then looking at our bottom problem, looking at number 12, if I plug in a 0 in for each of these x's, all the pieces that have x's cancel, and we're left with 0, negative 44 as one of the intercepts. So taking a look at each of these going up by 100, negative 44 would be halfway between 0 and negative 100. So because that's 0, negative 44, I am determining that that one is number 12. Just going to erase that instead of crossing it out. And then this one must be number 11. So the only thing I did there was figure out if there are a number of maximums and minimums and intercepts, and also the y-intercept by plugging in a 0 to determine where we're going with that. The next piece here is describing the end behavior of the polynomial function, and so we're going to use that notation in order to determine what's happening here. Ultimately, you can go ahead and graph each of these to see what's happening, and so that's what we'll do here. But there are tricks that we learned in Algebra 2 that helped us as well. And so we said that, for instance, if there was an even power, you end up having things end up together and begin together, or end down together and begin down. If you have an odd power, those are the ones that end up being opposites. And so if you end down or up, the opposite is true for the beginning. The other piece is that anytime that there is a leading coefficient that is positive, so we're going to say that LC is leading coefficient. So if we have a positive LC, we're going to end up with this guy here. If we have a negative leading coefficient, we're ending up with that one. Same thing is true over here. It is called end behavior, and so if we have a positive leading coefficient, we're going to end up, just as the previous one did, and then if we have a negative leading coefficient, we end down. So again, these are your side notes if you didn't remember them from Algebra 2. And of course, you can always just check by graphing. So either way. So number 25, we're given 3x to the fourth. Notice there's no negative out front, it's positive, and it's an even power. So because of that positive even power, I know that they're all going to end up. So writing out our limits as x goes to infinity of this function, we're going to go up to positive infinity. And then the opposite is going to be true for the other piece. Sorry, not opposite, just opposite in writing is also going to be positive. And again, the way that we're seeing this is that it ends up. But of course we don't write up, we write negative. Infinity. So the next one is number 26. Again, looking at what we're given, we have a negative out front for our leading coefficient, and we have a third power or an odd. So that means that we're going to be over here, and so our image is going to start in the... Okay, so it's a little hard. It's going to end down, and so that's this one here. And then this is your start. So taking a look at this piece, our start is up, so positive, so it'll be exactly this, but our end is negative, so it will be the opposite of that one. And so because of consistency, I'm actually going to write them the other way, because then you can see that this is the start of the function is going to be positive, and then the end of the function, as x goes to positive infinity, is down. And so again, this is the word for down. All right. Then in number 27, they're trying to trick you a little bit, because notice it's not in standard notation, and so it does actually have x cubed, or negative x cubed in number 27. So because it's negative x cubed, we are looking for the negative leading coefficient, so this column over here, and then also the odd power, so this image right here. So because it's the same as number 26, we can just say the same exact thing. So we're going to write that the limit of the start is up, and the limit of the end is down. And again, some of you may have gotten tricked by the fact that it's not in power order, so sorry. And then this one here is also not in power order. You see that we have an even power, and the leading coefficient is negative, and so we are going to actually have the opposite of number 25. Both of these will be negative infinity. So in number 28, both the start is negative and the end is negative. Okay. Then we move on to factoring, which may or may not have enough room on here. Looks like some of our variables are not x, so I'm sure I will forget, but you could use x or this number, that's fine. We only have 4 minutes left on this recording. Okay. So I think I'll actually pause this recording so that we just have bookwork as one video, and then we'll do this factoring as the next video.